Okay, we're going to continue on here, chapter 12, I think, if I'm not mistaken. All right, we've been talking about bonding in this chapter. So we talked about chemical bonding. And there really is two types of bonding that we talked about here. There is ionic bonding. And ionic bonding is always between a metal and a non-metal. And whenever those come together, we always get a transfer of electrons. And the result of that transfer of electrons is we will create some ions, and it is the metal that will always become positively charged because they're losing electrons and become a cation. Our non-metals here will become an anion, which is negatively charged. And once again, as we talked about, it's absolutely the electrostatic attraction that's holding that together. There is no sharing of electrons. In an ionic bond. So in ionic bond, we get a complete transfer of electrons. That is why we do get a kind of full positive charge, a full negative charge that happens because electrons are really transferring from one place to the next. And that's different than what we have in covalent bonding. In covalent bonding, it is two nonmetals. And because of all those periodic sort of properties that nonmetals have, and because they basically have very similar type of those properties and things like ionization energy, electronegativity, electron affinity, what happens is we get some type of sharing of electrons that occur. So that is definitely different than an ionic compound. There's no transfer of electrons, some aspect of sharing. As we talked about, there's really sort of two categories of covalent bonding. There is a polar bond, which basically means that the electrons are shared unequally. And there is a nonpolar covalent bond, which means that the electrons are shared equally. So a covalent bond, again, is the sharing of electrons between two nonmetals. And again, sort of two categories that fall underneath that covalent bond, either a polar bond or a nonpolar bond. And again, both basically describe how the electrons are being shared. At the end, we talked about how you can determine sort of, would you expect sort of equal sharing of electrons or unequal sharing of electrons? And really, we use electronegativity to help us do that. So we use electronegativity. And remember, there was a electronegativity value table, which runs from 0 to 4, and 4 being the most electronegative, 0 not so much. And it is fluorine that is the most electronegative. The general property of electronegativity is it increases up and to the right on the periodic table and decreases down and left on the periodic table. And we can take the difference in the electronegativity values, and that could help us determine whether or not we would expect the electrons to be shared equally or unequally. The cutoffs for the difference in electronegativity are approximately 0 to 0.4 is a nonpolar bond. So we would expect electrons to be shared, and we would expect them to be shared equally. Kind of 0.5 or above 0.4 to below 2 is some type of polar bond. So again, we would expect electrons to be shared, but unequally in this case. And typically above 2 is an ionic bond. Now, we did talk about a couple of things in terms of, do you always sort of need the numbers to help you out to determine things? And the answer is no, not in a lot of cases. You could just use a general trend in electronegativity to help you out. Especially with the ionic bond, as soon as you see it's a metal and non-metal, you really don't even need to kind of go to the numbers or anything like that. It's going to be ionic, so you could just put ionic and kind of move on with it. And as we saw, I think maybe we talked about last time, there are some combinations of metals and nonmetals that when you do the difference in electronegativity, it's actually less than 2. So the good thing for ionic, metal, nonmetal, that's all you got to worry about is going to be ionic. The other thing is as well, if you find yourself comparing 2 elements on the periodic table that's in the same period, which is a row, most likely going to be a polar bond, as they will definitely have differences in electronegativity, probably greater than the 0.4 level. Also, if you're comparing somebody in the same sort of group up and down on the periodic table, you can use the general trend in electronegativity and assume it's going to probably be polar. Again, comparing somebody in the same row, the one that is further to the right would be more electronegative. And obviously the one in the same group, the one further up, would be the more electronegative. And we can sometimes represent that, as we talked about, with those dipole arrows, like we talked about with HF. And the arrow always points to the side that is more electronegative. And the back side, it kind of makes like a plus sign, always to the side that is less electronegative. And that's for polar bonds. And that's because we also talked about, because there's that unequal sharing of electrons in a polar bond, there's sort of a positive side to the bond and a negative side to the bond, because the electrons are sort of heading towards one versus the other. In the case of fluorine, it's going to bring electrons towards itself, which means it's going to be more partially negative, as opposed to the hydrogen, which has electrons kind of moving away from it, which means that it will be more partially positive. Any questions on any of that stuff there we talked about last time? All right, so as we talked about and just reviewed there, atoms with really widely differences in electronegativity tend to form ionic compounds. And that's really why when we put metals and nonmetals together, they're basically on opposite sides, if you will, of the periodic table, which means there's a pretty big difference in terms of how they treat electrons. And that's why we typically get a transfer of electrons. Again, for our nonmetals, they are all pretty much sitting in the same spot on the periodic table. And that means that they all have super sort of similar sort of properties. The other thing that we talked about as well in terms of electronegativity was the diagonal relationship. So there are certain elements, which are different elements, that are diagonal on the periodic table, which do have the same electronegativity values. I think we did maybe carbon and sulfur. That sort of diagonal relationship cancel each other out. So it is possible to have 2 different elements that could be a nonpolar bond. But for sure, if you have 2 of the same elements, it should always be a nonpolar bond. But you can't have 2 different elements that could lead to a nonpolar bond. All right, so as we talked about there, our metal, nonmetal, ionic, and our 2 nonmetals being a covalent bond. So another way that sometimes people represent sort of polarity of bonds is they do sometimes talk about what is referred to as percent ionic character. And 100% ionic character means that you basically have an ionic bond. And a 0% ionic character would mean you really have sort of a non-polar covalent bond, sort of equal sharing of electrons. So sometimes people will say, hey, that bond is 100% ionic or 0% ionic. They sometimes will use that. Not a lot these days, but sometimes it does still sort of pop up in terms of the relationship there. And that's what we see here. So purely ionic or 100% ionic would be this way. 0% ionic character would be this way, as these guys would be sharing electrons equally. And percentage-wise, somewhere in the middle there, depending on what bond you're looking at, you have some type of ionic character. That is because there is still an almost transfer of electrons in a polar bond. And as we talked about, basically is referred to as a partially positive, partially negative charge, because there is still some aspect of sharing that's happening with those electrons. All right, so we talked earlier as well about drawing Lewis structures to represent ionic bonding. And a reminder that when we do draw Lewis structures to represent ionic bonding, You do need to include the charges, right, of those things. So when the guys make the positive charges, the metals, non-metals make the negative charges. You do need to include those charges because it indicates that there is no sharing of electrons. When we draw Lewis structures for covalent bonding, we do follow some different steps. In an ionic bond, we sort of, as we did, kind of could follow where the electrons are going to be transferred from the metal to the non-metal. In a covalent bond, which is really what we're talking about here, our covalent molecule, you do want to sort of follow these steps, and it should lead you to really sort of the correct structure. In most cases, are a really good structure. May not always be the best structure, but it should lead you to a pretty good structure. If you try to do Lewis structures for covalent compounds like you do for maybe ionic compounds, or maybe by piecework, drawing each individual sort of Lewis dot symbol, you oftentimes will end up with the wrong structure. You oftentimes end up with too many electrons, too many bonds, and things like that. So the first thing you want to do, or one of the first things you want to do, is think about how the compound is arranged. So what atoms are on the outside, which ones are sort of in the center when you go to draw it. To help you determine that, you pretty much can think about some rules. First rule is typically the least electronegative atom is in the center. And in a lot of cases, everybody else is sort of attached to that. Not always, but in a lot of cases, everybody else is sort of attached to the guy in the center. There can be multiple center atoms as well. But in a lot of things that you draw, in most cases, everybody will sort of be attached to the center guy. Hydrogen and fluorine should never occupy the center position when you're drawing a Lewis structure for two reasons. We talked about hydrogen, its need for only 2 electrons. So you can never put hydrogen in the middle, otherwise it's going to have way more than 2 electrons. So hydrogen, again, should always be, like we talked about the other day, pretty much on the outside. Something like that is pretty much what hydrogen should always look like in most Lewis structures. They should never have dots around them, just basically one bond in. Fluorine should never be in the center because fluorine is the most electronegative atom. So obviously the least guys need to be in the center. So fluorine would never be in there as well. Probably the most important thing that you do after that, or around the same time, is you want to count up the total number of valence electrons there are in your picture that you need to draw. Now, if you do have something that you're drawing that has a charge, that's an ion, you do need to take the charge into account. So again, if something has a negative charge, it means it has gained electrons. So you need to add that to your total, otherwise you're going to be off. And if something has a positive charge, you need to basically subtract that from your total number of electrons. That number is the most important number because when you are done drawing your picture, you need to have exactly that number of electrons on that picture. So you can't have any more, you can't have any less. It's got to hit exactly that number in order, hopefully, for it to be correct. Now, when we think about these electrons and when we sort of distribute these electrons, we think about it as like all the electrons sort of all the atoms get the electrons, not that any electrons belong to, say, one element versus the other. So sometimes where people get in trouble, they go, well, nitrogen has 5 and oxygen has 6. So try to figure out how they kind of come together. We just think about this as the total number of electrons we need to distribute over the entire molecule when we draw it. A reminder again that the number of valence electrons equals the group number. So that is the fastest way that you could calculate the number of valence electrons, is just to go to the group number. Once you got the logical arrangement for how everybody's connected, and once you got the total number of electrons, what you want to do is draw one single covalent bond from the center atom to each of the outside atoms. So if you use lines, that's basically one line from the center guy to each of the outside atoms. Once you do that, you're going to use up a certain number of electrons, and each line represents 2 electrons. So you can count up how many lines you drew, and you're going to subtract that total electrons that you use from the total electrons that you started with, and you'll have some electrons that are left over. All the leftover electrons will go on the outside atoms first in pairs of electrons, so 2 dots, until each of the outside atoms have 8 electrons, which meets the octet rule. Or if it's hydrogen, obviously no dots, because it should be done at that point. Now, if you've drawn your single bond from the center to the outside, if you distributed all the electrons on the outside atoms, and you still have more electrons to put on the picture, then you go to the center atom. And on the center atom, you put them on M pairs. At that point, you should be out of electrons, hopefully, at that point, once you put it on the center atom. And what you want to do at that point is, after you distributed all of your electrons, you want to make sure that everybody has met the octet rule. Obviously, hydrogen being the exception there. And it's really at that point, if they have not met the octet rule, you want to try to fix it. And the way that we fix it is we first try to make a double bond to fix it. And if that doesn't work, then we want to kind of move on to triple bonds. Once again, as I might have mentioned the other day, we really do not want to kind of double bond, triple bond, like right out of the box. You kind of want to do single bonds and save double bonding and triple bonding to maybe fix a problem that occurs if somebody has not reached octet rule. Any questions on that? All right, so let's go through one here together and see. So we want to draw the Lewis structure for NF3. So one of the first things I'm going to do is figure out the number of valence electrons. So nitrogen is group 5, which means it has 5 valence electrons. There are 3 fluorines. Each one's group 7, which means it has 7 valence electrons, and that is 26 valence electrons. So this is basically nitrogen from the periodic table, and that is fluorine from the periodic table. So I know when I draw my picture that my picture should end up with exactly 26 electrons. Again, no more, no less. Now, in this case, we have 1 nitrogen, 3 fluorines. The one that should go in the center in a case like this is usually the one element. It's usually the guy in the center. But we know that as well because nitrogen and fluorine are in the same period on the periodic table. And nitrogen's further to the left, which means it's the least electronegative. So nitrogen should go in the center. And the fluorine should be around it. Now, I put that last fluorine on the bottom. You could put it up on top. It really doesn't matter if you put it on top or bottom, but you can do it either way. So now I got my total number of valence electrons. I got my structure here with the least electronegative guy in the center. And now I'm going to make 1 covalent bond. In my case, I'm going to use lines, but if you do want to use dots, you can. But here I'm going to use lines to represent my bonding electrons. At this point, I made 3 single bonds. Each of the lines represent 2 electrons. So that's 2 times 3, which is 6. So if I subtract 6 off of my total, I have 20 electrons that I still need to put onto my picture. At this point, we're going to put them on the outside atoms until each one has 12. And again, they're going to go on as pairs of dots or electrons. So that's going to be 2, 4, 6, and that guy is going to be full. 8, 10, 12, and that's going to fill up that guy. 14, 16, 18, and that's going to fill up that guy. Again, they all have 8 there on the outside. At this point, I've used a grand total of 24 electrons. I still have 2 more electrons to go. I cannot put them on any of the outside ones now. So now we're going to go to the center atom and we're going to put it on there. And they are going to go on as a pair of dots or electrons. And now that would be 26 electrons at that point. Any questions so far? Now that I put 26 electrons, what we want to make sure is everybody has 8. So each of the fluorines, which are pretty much identical to each other, they have 2, 4, 6, 8. So they're all good. Now our nitrogens has 2, 4, 6, and 8 electrons. So it's good. So that would be the correct Lewis structure for NF3. Any questions on that? And you can see I treated the electrons as not belonging to anybody in particular. I distributed them evenly over the picture. And I did not like double bond or triple bond out of the box because it looks more chemistry-like. Yes. Any questions? Okay, so why don't you try one here? We'll see. that one. Well, we just did. Why don't you try this one, NO3 minus here. It's nitrate. All right, let's take a look and see. So once again, we're going to start with our valence electrons. So nitrogen has 5. Probably not the right one. There it is. All right, so nitrogen's got 5. We have 3 oxygens. Each are group 4. So again, that's our nitrogen, that's our oxygen. And now it does have a negative charge, which means should I add or subtract an electron? Negative means that it lost or gained electrons. Gained. So we do need to add an electron there for the charge so that we're not short. So that's going to give me 18, 19, 24 valence electrons in my picture. In this case, we have a nitrogen and we have an oxygen. So once again, if you look on the periodic table, we got nitrogen and oxygen in the same row. So oxygen should be more electronegative, which means it should be on the outside. Nitrogen should be in the center. So we're going to do a nitrogen in the center. We're going to do an oxygen on 3 sides. Again, you could put the other oxygen on the bottom if you wanted to. We're going to do 1 single bond to each of them. At this point, we have used 2, 4, 6 electrons. That means we got about 18 more to go when we subtract it off from our total here of 6, 18. These are again going to go on the outside in pairs. So that is 2, that is 4, that is 6, that is 8, that is 10, that is 12, that is 14, 16, and 18 at this point. Any questions on that so far? Now, at this point, I have used all 24 electrons. So the last thing I want to do is to make sure that everybody's good. They all have 8 valence electrons. Is everybody good in this picture? They are not all good. Oxygen is good. Each of the oxygen is 8, but the nitrogen in the middle actually only has 6 electrons, right? So our nitrogen in the middle has 2, 4, and 6. So it is short the number of electrons. So this is a case where we need to fix it. Can I just put a couple of electrons there to fix it? I cannot, because now my total number of electrons is 26, which is too many. So we cannot just add electrons to do it. What we need to do in this case is we actually need to fix it by first trying to make a double bond. Now, can I just double bond at any of these oxygens? They're all the same. So can I just lay a line up in there as well? I cannot for the same reason, because if I do it like that, a couple of things, I now have 26 electrons. Oxygen up on top has 2, 4, 6, 8, 10 electrons, which is too many electrons. So in a situation like this, when we need to kind of fix it and make a double bond or attempt to fix it by making a double bond, what we actually need to do is take a pair of electrons that are non-bonding electrons and basically bring them in. And in this particular case, you could have done it at any of the oxygens because they're all exactly the same. So you could have took a pair of electrons from any of the oxygens and bring them in. When you do that in the way that I just did it, you will end up with a nitrogen that has a double bond to the oxygen. The other oxygens will also still have their single bonds. And by the way, since it is an ion, we do typically put brackets around it and the charge on the outside to make it look prettier. But at this point, if we go around, everybody has 8 electrons, and we still only have a maximum of 24 electrons, which is what we need. So if we count it up real quick here, oxygen here has got 2, 4, 6, 8 electrons. Same thing here, 2, 4, 6, 8 electrons. Oxygen on top, 2, 4, 6, 8 electrons. And nitrogen here in the middle, 2, 4, 6, 8 electrons. So once again, everybody has met the octet rule by sharing electrons. And to do it, we needed a double bond here off the bat. Question on that there. Now, if you did sort of double bond to the left or double bond to the right is perfectly fine. Your picture would just look like this if you had double bonded over here. And if you double bonded to the right there, it would look something like this. And in this case, you do have a few options as to where to double bond it. And all three of these structures are actually related to each other, and they're usually related by that arrow kind of heading in both directions. These are what are known as residence structures. And residence structures really do occur in this situation where you have really more than one option as to where you could lay up the double bond. So you could actually draw three equivalent structures here for this guy. And they're all basically the same. And the reason for that is the double bond electrons are what are referred to as being delocalized, which means at any given point in time, you know, they may be kind of hanging out over here at this oxygen, but maybe they're over here at that oxygen, or maybe they're on that side at that oxygen. So you could draw three equivalent structures, which are known as resonance structures of each other. If you were not asked to draw resonance structures and you were just asked to draw a Lewis structure, you could lay up any one of the three pictures and they're all perfectly good, whichever one you want to lay up. But if you're asked to write all the resonance structures, you should draw pretty much all three structures. Pretty much to draw a resonance structure, you just move the double bond to wherever it possibly could be. Any questions on that one there? So again, here we didn't double bond or triple bond out of the box. You do want to kind of save that to fix a situation that may occur. All right, so why don't you draw some here? Let's go with let's do H2S. Let's do N2. Let's do CO2. Let's do CO3, 2 minus. Let's do nitric acid for fun. Nitric acid actually has a couple central atoms, so I'll give you kind of the way it's hooked up. It looks something like this. One of the hydrogens is hooked up to an oxygen. All right, so take a few minutes here, draw up these guys, proper Lewis structures for each of these. See what you come up with. Okay, let's take a look, see how you're doing on these. So we'll start at top left here. So once again, I'm going to count up the valence electrons, which is most important. We have 2 hydrogens, and hydrogen is 1. And then sulfur is group 6, which means it should have 6. So in this case, we're looking for a total of 8 valence electrons in our picture. Once again, here we know hydrogen should never be in the middle, so it's going to be sulfur that should be in the middle. And again, we'll put our sulfur in the middle, our hydrogens on either side. And at this point, we're just going to connect it with one single bond, which I'm going to represent with a line. So that is 4 electrons that have been used, and obviously we subtract 8 and 4. We're left with 4 leftover electrons that we need. Can I put any more on the hydrogens? I should not. So really the hydrogens on the out are filled. Should never put dots around them. So that means that those 4 electrons then need to go to the center atom, and they will be placed on as pairs of dots. So that is 2 and 4. At that time here, we have now placed all 8 valence electrons, and we could check to make sure everybody's good. So each hydrogen obviously has 2, which is the most it should have. And the guy in the center there, which is the sulfur, has 8 electrons. Again, doesn't matter if they're lines or dots, we're counting the total number of electrons. So it's got 2, 4, 6, 8, 4 for the lines and 4 for the dots. Any questions on that one there? Coming to our nitrogen here, there are 2 nitrogens, and each nitrogen is group 5. So that is 10, I believe, electrons there, valence electrons. In this particular case, it's a diatomic molecule, so there really is no central atom. So we're just going to kind of put them side by side in this case. And even though there's really no central atom, we could still follow the same rules that we did before. We're just going to connect them with a single line. So we're going to do a single connection there. That is 2 electrons, which means that it has 8 electrons to go. So we're also going to continue to do the same thing. We're going to put all those electrons on the outside atoms in pairs until they're full. So that's going to be 2, 4, 6, and that should fill up that guy. And then 8. At this point, though, I am now out of electrons. I have put 10 electrons on my picture. Are both nitrogens good? They are not, right? The guy on the left there is short. He has only 4 electrons on the left. Guy on the right's good. He's got 8. So again, this is a case where we're not going to add any more electrons. Otherwise, we'll have too many electrons. So we're going to try to fix it by making a double bond. And we're going to do exactly what we did on the previous slide there. We're going to take a pair of electrons and bring them in. And if we do that, we would then get something that looks like this. If we did it step by step here. At this point, did it fix the guy on the left? It didn't, but he got better. He's up to 6 now, right? And the guy on the right still has 8. So at this point, there's no other possibility to make a double bond. So we can't make another double bond, obviously. So now we want to move to a triple bond to try to fix it. And the triple bond works the same way. We're going to need to bring in a pair of electrons to make that triple bond. So again, we'll take a pair of electrons and bring them in to make the double bond, or triple bond in this case. And if we do that, we will end up with something that looks like this. And now this guy here, which should be our final structure, has 8 electrons on both nitrogens by sharing electrons through the triple bond. And we still only have a grand total of 10 electrons. So that is how nitrogen actually gets to a triple bond, by doing that sort of process there. Any questions on that there? You mean how I have the dots on top? It doesn't matter as long as the nitrogen on both sides has only 2 dots. So you could have them on the top, you can move the dots to the side or on the bottom. But again, I cannot have in this case any more than 2 dots. Yeah. And they should always be together. So they should always be pairs of electrons when you put in them. Never put them as ones or anything like that. So they should just kind of come on as pairs. Other questions? Okay, looking at CO2 then, carbon is group 4. There are 2 oxygens, which is group 6. That's like a lot of math there. That's 12, that's 16 valence electrons in this case. Between carbon and oxygen, who should go in the center? It's actually carbon should go in the center, because if we look at the periodic table, carbon's here, oxygen's here. So oxygen is further to the right, and it's the most electronegative. So that would mean that carbon is the least electronegative. And also in most cases, like I said, if you have kind of like just one atom of an element and multiples of others, usually the one atom ends up in the center. So we are going to do carbon here in the center. We're going to do some oxygens on the side. We're going to do our same process here. So that is a single bond to each of those. That is 4 electrons, which means we have 12 more to go. So that's going to be 2, 4, 6, 8, 10, and 12 at this point. Now we have displayed a total of 16 electrons. Is everybody good in this case? Yeah, it's not. So the carbon in the middle has only 4 electrons. So we're going to try to fix it by making a double bond. In this case, each of the carbons are the same. So you could do the double bond from either one. Again, I'm going to take a pair of electrons in to do that. And that would give me a double bond on the left and a single bond on the right. Did that fix the carbon? It did not. Once again, it got better. It's at 6 now, but it's still short of 8. So at this point, I actually do not want to jump to a triple bond, because I could still make a double bond on the other side. So you kind of want to exhaust all your double bonds before you decide, hey, I want to jump into a triple bond. So at this point, I'm going to actually do a double bond on the other side. And again, same deal. We're going to take electrons and bring them in to do it. And that will give me a double bonded oxygen on the right and a double bonded oxygen on the left. And at that point, we should be good for everybody. Everybody has 8 electrons. And again, we still have only a grand total of 16 in this case. That's what we're looking at. Any questions on any of those there? All right. Now, could you have made a triple bond on the left and a single bond on the right? The answer is yes, but there's something known as formal charge, which we might talk about, but probably not too much in this class, which tells us that actually this structure that we're looking at is actually the better structure. That's why you typically want to kind of run through all your double bonds before you jump to a triple bond. All right, let's take a look at the last few here. I'm just going to flip the page so I got a little bit more room to draw these. We'll go with CO3 2 minus. And once again here, that's carbon, which is 4. There's 3 oxygens, which are 6 each. And here we have a -2, which means that it has gained 2 electrons. So we want to add 2 electrons to it for the charge. Otherwise, we're going to be off. And that's going to be 18, 20, 24 valence electrons. Here, carbon is again going to go in the center with our oxygens around. Going to do a single bond to everybody. So that is 6 electrons, and we got 18 more to go. Again, as pairs, so 2, 4, 6, 8, 10, 12, 14, 16, and 18. Once again, we have now placed all 24 of our electrons, and we again see that our carbon there in the middle is short. So we're going to fix it here by making a double bond. And once again here, you could double bond at any of the oxygens because they're all the same. I'm going to do the top one. So I'm going to bring those electrons in to do it. And that would give me a double bonded oxygen up on top. And single bonded oxygen coming this way. And once again, because it does have a charge, put a little bracket and the charge out on the outside. And again, here we have now got everybody to 8. And we have only 24 electrons. This is another one where you could draw some resonance structures for by making the double bond at different location. So if you double bonded to the right, it'll look something like this. And you could draw one more resonance structure where you would double bond it to the left here. So once again, these are the 3 resonance structures that you can draw for this picture. But if it was a question of just draw a Lewis structure, any one of the 3 is perfectly good. Any questions on that particular one there? So lastly, or semi-lastly, we have NH4 plus. So nitrogen is 5. There are 4 hydrogens, each at 1. In this case, we have a plus charge, which means we need to subtract 1. Yeah, again, it lost an electron, so we got to take 1 off. So that's going to give us basically 8 valence electrons in this case. And to draw 8 valence electrons, nitrogen will go in the middle. Hydrogen will go around. Going to do a single bond to each of the hydrogens. And that is 2, 4, 6, 8. That looks like it. Yeah. Hydrogens on the outside are good because they have 2. Nitrogen on the inside is good because it has 8. Just put a little bracket and a little plus next to it, and you would be good on that one there. Any questions on that one? All right, the last one, which I kind of gave you the structural formula, which I will if it's something I don't think you would be able to figure out, was nitric acid, actually, HNO3. And nitric acid has 1 for the hydrogen, 5 for the nitrogen, and 3 times 6 for the oxygens. That's 18, 19, 24 valence electrons. Once again, the arrangement of this guy is one of the oxygens has a hydrogen attached to it, which is what makes it an acid. We'll talk about that in a later chapter, but it looks something like this. So even though there's kind of 2 central atoms in this case, the nitrogen and the oxygen, we still follow the same procedure. We're going to connect everybody up with a single line, basically. So just a single bond to everybody. At this point, we have now used 2, 4, 6, 8 electrons. That's 16 more to go. We're still going to follow the same procedure, outside then in. So outside would be hydrogen. Should I put dots on the hydrogen? No. So we're going to put some dots here. So that is 2, 4, 6, 8, 10, and 12. Next outside one would be the oxygen. That could take a few. So 14, 16, I think, at this point. At this point, I have now put on there 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24 electrons. Is all the elements good here? The nitrogen in this case is actually not good. So even though there's multiple kind of central atoms going to work the same way, we could actually make a double bond at any of the oxygens. The one most likely you would not probably touch in most cases is this one. That's really what makes it an acid, is that hydrogen coming off. So you most likely would probably double bond one of the two other oxygens. And the same thing will happen. We'll take a pair of electrons and bring it in. And in this case, we would end up with something that looked like this. Or if you draw bigly this way, drew another resonance structure, maybe it would look something like this if you double bonded to the left. And now everybody has 24 electrons total, and everybody has 8 except for hydrogen that has 2. Any questions on that? So even as we saw in some of these examples, it's a diatomic, just no central atom. You still follow the same procedure. Even if there's multiple central atoms like this guy, where the nitrogen and the oxygen are considered central atoms, you still follow the same procedure. And if you follow all those procedures, you will in most cases end up with a pretty good Lewis structure. Again, not perfect all the time, but in most cases, you'll end up with a pretty good structure. Any questions on the steps to follow when you draw Lewis structures? Yeah. So clearly you need to be able to do this. I was thinking, yeah. All right, so we did that guy here. All right, so we talked a little bit about resonance structures, but also a couple other things about bonding, bond length. So this is the table bond lengths, and by no means do you need to memorize it or anything like that. But what we do look, if we look at the single carbon-carbon bond, the double carbon-carbon bond, and the triple carbon-carbon bond, the distance between the two atoms goes from 154 to 133 to 120. And if we look at carbon-nitrogen, single, double, triple, goes from 143 to 138 and 116. What we see is, as we keep adding a bond, does the distance between the atoms get further or smaller away from each other? They actually get smaller. When you bring those electrons in, everybody becomes a little bit tighter. You bring another one in for a triple bond, they come closer to each other. So every time you bring those electrons in to make a double bond or triple bond, it's just going to bring the attractions from everybody closer to each other. And the distance between the atoms gets smaller and smaller. So that is the general trend of what you see when you add a bond. The length gets smaller. That does relate to the strength as well, because now the atoms are much closer together. A triple bond is stronger than a double bond, and a double bond is stronger than a single bond. I sort of related to like a pencil, right? If you got a brand new pencil out of the box, you could take it and snap it pretty easy, right? There's a good distance between each end. If you take a couple chemistry tests, you got like a nubbin and like an eraser at the end. It's super hard, right? If you got a really small one to try to break it in half, everything is much closer together and held tighter. And that's sort of the same idea as what we see here with bonds. A double bond is not like twice as strong as a single bond, or a triple bond is not twice or 3 times as strong as a single bond. But that's the general trend that you see. Single bond longer, and a single bond is weaker than a double bond or triple bond as you go through there. Any questions on that there? All right, so we talked about resonance structures here as we were drawing our Lewis structures. And again, a resonance structure is really drawn for a situation where two or more Lewis structures can be drawn because of that really option as to where you can make the double bond. And basically the only real difference between each of those Lewis structures or resonance structures is pretty much where you place the double bond. And again, that's because those double bond electrons are again delocalized. So they're sort of kind of flowing around from atom to atom, and you're able to draw different Lewis structures based on that. And here's a few examples that some of which we saw. That's ozone, which has a double bonded to one oxygen and a single bond on the other side. So again, basically the only difference between structure on the left and the structure on the right is the placement of where you made the double bond. And obviously we just did our carbonate example there. You can ignore the charges on each of those atoms, but that's the only difference. Double bonded up here, double bonded to the left, or double bonded to the right as well. The benzene ring is an organic molecule that has actually 3 double bonds, looks something like this. And you could draw a resonance structure that looks something like this. And at each of those points are carbons, and there's basically a hydrogen at each of those points. And it's got the double bond that basically happens in that case. It's an organic molecule, and sometimes because those electrons are moving around the ring, sometimes in certain organic books, they'll even just draw the benzene ring with like a little circle in the middle to indicate that the double bond electrons are basically moving around. Any questions on that there on resonance structures? All right, and same example here. We'll just kind of skip through it in case you want to look at it. You can. Same idea. All right, now there are some exceptions to the octet rule. And I will say in our class here, we won't draw any exceptions to the octet rule. When you get to 1A, you'll draw a bunch of exceptions to the octet rule. But here we'll obey the octet rule, but you should know what the exceptions are. But again, anything that you draw in here will probably obey the octet rule. One exception to the octet rule was referred to as an incomplete octet. An incomplete octet means that it will actually be okay with less than 8 electrons. And for the most part, even though this maybe doesn't really exist, boron is really your guy that's perfectly fine with basically 6 electrons. Is what is sometimes referred to as being electron deficient because it sort of has less electrons. But boron is probably the most common example that you come across. So if you see something with boron, it can be fine with less than that, and it usually ends up at 6 electrons to make it sort of happy. Another couple of important exceptions to the octet rule. One is a odd electron molecule. That is when you basically add up the total number of electrons and you get an odd number, which again will not happen in this class, but it can happen in real life. Maybe you've heard of free radicals, which are basically a lot of times guys that have 1 unpaired electron. They're very much reactive because they have 1 unpaired electron. They're not really happy about that, so they want to kind of fix that situation. So a lot of atmospheric chemistry with chlorine has a lot of guys that have like 1 free electron. And as you can see here on the nitrogen and NO and NO2, we have 1 unpaired electron. But once again, you will never be asked in this class to draw anything that is that, but that is an exception to the octet rule. The most famous exception to the octet rule is the expanded octet, and that is the one that you'll see a lot when you go to 1A. They draw a bunch of expanded octets and stuff like that. So an expanded octet is, as it sounds like, it is something that can actually have more than 8 electrons. So it's perfectly good with more than 8 electrons around it. Starting at sulfur on the periodic table, to the right, to the left, and down where our nonmetals are, Those are the guys that actually can go above 8. And the reason they can go above 8, it has to do with the electron configuration stuff. Sulfur, which is on period number 3 of the periodic table, which means it's on the 3rd energy level. In terms of orbitals, what orbitals are available on the 3rd energy level? There are S's, P's, and it's the 3rd energy level where D's start to occur. So because they have D orbitals available to them, even if they're not using them, they have places to store the extra electrons. So anybody that is like sulfur left and right and down has the D orbitals available to them, which means they can actually go above 8. They could go upwards of having 12 electrons around it, 6 bonds, 12 electrons around it, and that's an expanded octet. That also means if you look on the periodic table, like at anything like carbon, nitrogen, oxygen, they're in period number 2, which is the n equals 2 level. On the n equals 2 level, there's only s orbitals and there's only p orbitals available, which means they can never ever go over 8. So anybody above sulfur on the periodic table can never go over 8 electrons because they don't have the d orbitals available to them to allow them to do it. So an example like SF6 is an example. So if we just draw it out real quick, it looks something like this here. 3, 6, and then obviously all the fluorines will have dots around them. And if we count up the electrons around sulfur, has 2, 4, 6, 8, 10, 12 electrons, and it's perfectly fine to do that because it has those d orbitals available. Once again, you should never ever draw it over that. Also, how somebody would know that you were just looking online for the answer when you were asked to draw something like sulfate if you end up with this picture. With a couple of double bonds on sulfate, that is the Google answer, which is not the answer you should get if you followed what we just talked about, how to draw it. So if you follow the octet rule, you will not end up with a picture that looks like that. You'll end up with all single bonds. So make sure in this class you follow the octet rule and our rules. You'll learn in 1A that actually that picture is actually the better picture than the single bonded version, but for our purposes, you should draw the single bonded purpose there, or way of it. Any questions on exceptions to the octet rule? So once again, we will follow the octet rule in this class, where anything that you draw, you should follow the octet rule. You should not go over 8, even if it is sulfur and below, you should still stick to keeping it to the right amount. And you just need to know what the 3 exceptions to the octet rule are. You don't need to actually draw any, I think. Any questions on that here? We'll save that for 1A when you get there. All right. I think that might be a good place to lay it up, and we'll figure out geometry on Wednesday, I think.